Hello everyone. In this video, we will go through two experiments of the SRV02. The first one is the position control. In this lab, we want to develop feedback systems that control the position of the rotary servo load shaft by using the PID control. This servo plant has a DC motor that is encased with a solid aluminum frame and a planetary gearbox. It has three sensors: potentiometer, encoder, and tachyometer. The potentiometer and encoder sensors measure the angular position of the load gear, and the tachyometer measures velocity. Before we start the experiment, please read the lab workbook and complete all pre-lab questions on section 2.2. The main goal of this position control lab is to explore position control of the SRV load shaft using PV and PIV controllers. In this lab, we will conduct three experiments: step response with PV controller, ramp response with PV controller, and ramp response with no steady-state error. First, we will use the Simulink model, shown on the first image, to simulate the closed-loop response of the servo with a PV controller to a step input. We want to confirm that the desired response specifications in an ideal situation are satisfied, and to verify that the motor is not saturated. Then, we will use a high-pass filter to create the velocity signal V in the controller. The second image is the PIV controller from the blue block, and the green block is the motor model. This is an enlarged image of the position control Simulink diagram. The first block is the signal generator. That's where we enter the parameters of the signal input. The second block is the amplitude gain block to generate a step with an amplitude of 45 degrees. The blue block is the PIV control block. The green block is the SRV02 model block. It uses the transfer function block from the Simulink library. And yellow blocks are scopes to display responses. This is an enlarged image of the PIV controller. This diagram represents the transfer function of theta 1s over theta ds. To set up the simulation, we need to enter the proportional and velocity control gains found in the pre-lab question 4, SKP and KV. Then, set the signal type as square, amplitude as 1, and the frequency equals to 0.4 Hz. And set the amplitude gain block to pi over 8. Inside the PIV control subsystem, set the manual switch to the upward position so the derivative block is used. And start the simulation. The scope are displaying responses. The yellow trace is the set point position, while the blue trace is the simulated position. The scope on the left is the ideal PV position response, and the scope on the right is the ideal PV motor input voltage. This MATLAB figure shows the ideal PV position responses and the ideal input voltage. Use the data to answer questions in the workbook. The next step is to use a high-pass filter instead of a direct derivative. Go in the PIV control block and set the manual switch block to the down position to enable the high-pass filter. This MATLAB figure shows the filtered PV position and the input voltage responses. The next step is to implement step response using PV controller. In this experiment, we will control the angular position of the SRV02 load shaft. The load shaft is a disk load. The diagram on the right is used to implement the position control experiments. The orange block represents the real physical motor. And we use the same setup as before. The video on the left is actual servo motion. The recorded data will be provided for analysis. The video on the right shows the measured load shaft position and the motor input voltage. The next sub-experiment is the ramp response using PV controller. We want to verify the system with the PV controller can meet the zero steady state error specification without saturating the motor. We use a similar setup as before. Set the signal generator parameters to generate a triangular reference. First, run the MATLAB script, then enter the Kp and Kv found in the pre-lab. Set the signal type as triangle, amplitude equals to 1, frequency equals to 0.8 Hz, and set the amplitude gain block to pi/3. Set the manual switch to the down position to use the high-pass filter. This video shows the simulation of the ramp response. The left scope is the ramp response using a PV. The right scope is the input voltage of ramp tracking using PV. This MATLAB plot shows the ramp PV position response and its corresponding input voltage trace. Use the data to answer questions in the workbook. The next sub-experiment is implementing ramp response using PV. The goal is to examine how well the system can track a triangular position input. We use the same setup as before. This video shows the responses collected from the load shaft. The left scope is the measured PV ramp response, and the right scope is the input voltage of PV ramp response. And this MATLAB plot shows the ramp PV position response and its corresponding input voltage trace. The data will be provided to answer questions in the workbook. The next sub-experiment is the ramp response with no steady-state error. We want to design an experiment to see if the steady-state error can be eliminated when tracking a ramp input. First, answer the questions in 2.3.3 and design your PIV controller. This video shows the simulation of the ramp response and the input voltage using the PIV controller. This video shows the actual shaft response from the PIV controller. The data will be provided to generate MATLAB plots. These MATLAB plots show the results from the simulated and actual measured PIV ramp response and the input voltage using PIV control. Please read Laboratory 2 SRV02 Position Control in the Rotary Servo Base Unit student workbook, analyze the provided data, and complete the lab report outlined in 2.5. For the second experiment, we want to develop feedback systems that control the speed of the rotary servo load shaft by using the PI control. Before we start the experiment, please read the lab workbook and complete all pre-lab questions on section 3.2. Our goals are to confirm that the desired response specifications in an ideal situation are satisfied, and to verify that the motor is not saturated. We will use this Simulink diagram to simulate the closed-loop speed response of the SRV02 with a PI controller to step input. This is the PI controller used in the PI compensator block. The values of Kp and Ki are used in here. We need to set the signal generator block parameters as this. Set the manual switch to the upward position to activate the PI control. This is the Simulink model used to run the PI controller on the SRV02. The simulation runs for 5 seconds. The left scope is the simulated PI speed response. The right scope is the simulated PI motor input voltage. This MATLAB plot shows the simulated PI response. Use the data to answer questions on 3.3.2. The next sub-experiment is implementing PI speed control. The SRV02 ET block is the interface between the DC motor and sensors. We use the similar setup as before. Remember to set amplitude gain block to 2.5 radius per second, offset to 5.0 radius per second, and set the manual switch to the upward position to activate the PI control. The video on the left is the measured response. Run the simulation for 5 seconds. The left scope is the measured PI step, speed step response. The right scope is the PI motor input voltage. The video on the right is actual SRV02 movement. This MATLAB plot shows the measured PI speed step response and the PI motor input voltage. Use the data to answer questions on the workbook. Due to the noise in the measured speed signal, it is difficult to obtain an accurate measurement of the specifications. So we set the amplitude to 0 radius per second and the offset to 7.5 radius per second to generate a constant speed of 7.5 radius per second. And this plot is the noise in measured speed signal. Use the data to answer questions from the workbook. Please read Laboratory 3 Speed Control by PI in the Rotary Servo Base Unit Student Workbook. Analyze the provided data and complete the lab report outlined in 3.5.1. This is the end of the video. Thank you for watching, and the details about the report will be posted on Blackboard.